Okay, in this video, I'm going to demonstrate how to prove that RMS value is an equivalent DC voltage for the AC waveforms. Okay, so first, let me just open a new live script, and then we'll do close all, clear all, close all, CLC. To clean this whole thing up. So we clean this workspace. It's a good habit always to clean up your workspace and the command window. And then our next section, I'm going to copy it from our previous demonstrations, how to draw a sine wave. So when I run this section, you'll see that it basically produces a sine wave. But this time I only do one cycle. As you can see, this is one cycle, and then I plotted 10 points. You can see this points 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we produce these 10 steps, so that will be 11 points because this is the step size. It go from 0, so 0 is the first point, and then after that you have 10 more points. So you can see that if you only use 10 points to plot a sine wave, this is not really look like a sine, right? So we usually say do 100. If we do that, you can see red section. You see this is much better approximations, but if I took this out, I can click this, and then this will be pop up. I have a do monitor, so it popped up to my other monitor, but I just put it back. You can see that if I do 100, this is a much finer representation. So these points, they represented the steps between this 2 points. That's very small. So if you use this staircase to represent these curves, they have lesser and lesser arrows. But if I only have 10 points, you can see that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Then the sine wave can only be linearized, right? Connect these points together, so it's not really a good representation for sine wave. Suppose I want to do more finer detail, I can do 1000. So if I run that, and then bring this back, we'll see you have an even better representation. Let me just delete out this curve. This, oh, okay, it's all out, but let me just clean it out. Clear it up. So we just run the whole thing again, and then you will see that, let me bring this, you hit this one, this window will be popping up. It will be separated from this display column. And then now we can see that when we have 1000 data points in a cycle, from here we have 1000 points. It's a much, much better representation. If we zoom in, you can see that this kind of level of approximation, the arrow is very small now. Okay, let me close that. So as I said, right now we can just plot out a sine wave. So now we're going to see if we have a DC representation. We use this RMS value, then we will have a DC voltage, right? So we have DC voltage, then what it will look like, whether or not they will produce the same results. So if I have a DC here, I basically can do VA C equals to VA RMS times 1's. Okay, so T here is this is the column wise is the length, so I want to have the same length as T, and then column wise I only need a one column. So this way what I'm going to do is I'm going to create a matrix here. So this will give me a matrix which is from 1 to the length of T. So this T is actually a vector. You have 1, 0, 1 rows, right? You only have one column. So this is 1, da, 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 until for the row 1001, it also has 1. So I use this to times the RMS value. So this will give me a DC because the value here remain the same, right? So let me see if that will be the case. Okay, so let me run this here. So we will plot T, B, A, DC using, let's say, blue. Okay, so let me run that. You can see here when I run it, this is my RMS value for this. This is my peak value. That's the RMS value times square root of 2, right? So let me clean this up. Okay. So now I have this is my RMS value. So what I'm trying to prove is that for this entire cycle, when I consume the energy here, this is the energy that I would have consumed when this voltage, this AC voltage, it is supplying a resistor. Say this R equals to 10 ohm. Okay. Then whether or not that will be equivalent, this will be equivalent to using a battery to supply a 10 ohm resistor. Okay. So this voltage will be this purple one, right? This AC voltage will be this black one. Okay, so let me try to prove if that's the case. So for us to do that, we will start a new section, and then we'll let EAC equals to 0. So that means that the initial energy is 0, and then R equals to 10. Okay. And then now I'm going to do a for loop for I equals to 1. Step size is 1. And then the index will go through all this T times steps, right? So the total length of T is 1001 if we use 1000 intervals, right? So I'm going to go through 1001 iterations. So each iteration, what we're going to do is that we have BACT. So this will be the instantaneous value. That will be the absolute value of VA RMS times square root of 2. And times cosine omega times the T of I. So you can see that T is no longer a matrix. We get to the ith element of T. So we will plus, let's say we have an initial phase angle at 0 to start with, and then we do that. And then this is our voltage, because this is an impedance, right? So a resistor. So we'll each time we'll consume energy, we add it up to the original energy is 0. So after each interval, for example here, oops. Let's see. Need to find out my clear it up for some reason. Okay, good. Back to business. So now let's unfortunately I need to redraw that. Okay. So we have an AC here, and then we supply a resistor of 10 ohm here, and then we have a DC here. We supply a resistor of 10 ohm. Okay. And then this is my DC voltage, and then this is my AC voltage. Okay. And then the initial angle is 0 because I started from 0 here. So this at 0, my cosine peak right? So this is my maximum voltage right here. And then this maximum voltage here equals to 120 times square root of 2, right? So if I want to compute it for an instantaneous value, I simply times cosine omega t plus theta. So here theta is 0, so I just have 0 degree. And then this t, if the t equals to this value, then you simply just times this value. So that's our t of I, okay? So these are how I'm going to do the instantaneous value. So now when I have this, I can have each time I'm going to have V A C T, the square of it divided by R, and then times delta T. The reason that we need to time delta T is because we want to compute for the energy, right? So this delta T will be the interval. So that means that what I'm going to do is say each time when we compute this value here, it has small interval here. So this interval, when I times the this height with the width, that will be the energy consumed during this interval. And then that interval is simply the step I'm going to go from one to another. For example, the next one, it probably will be like this. Okay, so this is how I computed the energy. So this energy simply will be V squared and divided by R. So this V is the instantaneous value at this particular point. Okay, so that's how I compute for the energy and sum them up. Okay, so after that, I'm going to compute it for the DC. So DC is easy. E DC equals to VA, that's RMS value, and then it is a square, and then it's divided by R, and then times ln T. Okay. So here I directly times length T is because when I do this, this entire interval, the DC voltage simply consumed this much energy. So this is length T. So this, the whole length is length T, okay? Because the DC value here is the same for the entire length. So the energy I consumed will simply be the length times this, right? And then this, because right now this is voltage, and then if we want to compute for a current or the power, it will be V squared divided by R. Okay, so this is how I do that. And then after I have those, what I'm going to do is I'm going to plot them out, figure 2. And then this time I'm going to use a bar plot, so it will be 1 and 2. So I have the 2 bars that I want to compare. So the first bar is the EAC, and the second is EDC. Okay, so that's what I'm going to compare. And then if I want to also say, hey, I want to have let me just clear them out just so you have an idea what will be there. Let me just clear this up. Yeah, this is bar. Let's fix that. And then run it. Okay, so let me clean this up. The annotation, clear out. So you can see that this is the AC energy consumed in this entire period of time. So that's the area of these. Okay, so that's that. And then this is my DC energy. So that DC energy will simply be this. Okay, so we proved that these are very similar. So right now, let's do one more thing because we can always see exactly what our value is, right? Oh, by the way, we can do one more thing to make it clear because I can label this. I use set GCA. So GCA is basically the alias of this figure. And then I set the artistic label to be the name, okay? So when I have the name, I have the name as here. So the name is EAC and EDC. So this is more like a latex representation. So when you have subscript, you put them into the this parenthesis that now be giving us this, right? So you can see this is a subscript, and then you put them in here, it will be the subscript. So this is EAC, this is EDC. So this is the AC energy, this is the DC energy. So the last thing that we can do is just say, hey, I want to know exactly what the difference is. So I do EAC minus EDC. So that would tell us what would be the actual differences, right? EAC. Oh, I didn't have this. Okay, so EAC, so there will be AC and EDC. Yeah. So this means if I use here EAC minus ADC, so this value will give me the arrow between that. So you can see that this arrow currently is pretty small. If I run it, you can see the arrow. Here is only 0.048. So if I change this to say 10, what will happen? Let's run that again. You will see this arrow is big. The arrow is big here is because you can see that when I'm running this representation, this AC is no longer a curve. It's represented by these stairs. So compared with this actual AC curve, if I use this square, use these bars to represent this area, it will give me a larger arrow, right? So the finer these points are, the difference this difference should be smaller, right? So remember when we have 1,000 points, this would be 0.048. So suppose we have even more, we have we have 10,000 points in there. Let's see how much the arrow we can compute for this two energy. So now you can see this arrow is even smaller, right? So this shows us that when we have this representation, this RMS value indeed is this is how you do integration, right? So with this, there are more points in there. You will see that this will be eventually get to equal when it's approximate to really small intervals between these two points. Then these two values will be very close to each other. Okay, so this demonstration just shows you why we can actually represent this AC curve by RMS value, because this RMS value basically is representing the equivalent DC voltage. That means that inside a cycle, if you supply a resistor, with this AC voltage, it is equivalent to say you have a DC voltage of this RMS value, you will consume in a cycle the same amount of energy. Okay, so that's what I want to show you. So this also show you that when you have, you can program in MATLAB, you can sort of like play around with that. So it will let you build a model and then illustrate how this compute calculation is done. Okay, so I'll see you next time. Thanks for watching.